Hi, welcome everyone. So what we're going to be talking about now is phase change diagrams. We're going to talk about phase change diagrams and what a heating curve is. So first thing is, a phase change diagram is showing the pressure and temperature at which the substance exists. And we're going to be looking at the solid, the liquid, and the gas states of a different substance. Every single substance will have a different chart. So it's not like you would look at a chart and be able to use one chart in order to figure out what the values are for carbon dioxide when you're given water. Water has a very specific and very different type of plot. And so I can recognize water really easily. And I always say that water actually has open arms because water loves us. We love water. And so water has open arms. This opening right here that we see with water is very, distinctive, and it tells us what the graph is. Now I'm going to explain that in 1 second. I told you that we were going to come back and I was going to ask you on a test, so let's do it 2 more times, what the units were, what the axes were on a label for a graph. So don't say anything. What I want you to do is just write line versus line, and on this graph I want you to just really quickly write what the 2 labels would be that would fit in there. Okay, on the count of 3, remember we actually read in English, we read left to right. Okay, you got this? Yeah. On the count of 3, what are your axes? 1, 2, 3, what versus what? Say it.
Pressure versus temperature.
Nice, it is pressure versus temperature. Awesome, love it. Okay, so that's going to be the label for your axes on this graph. Flip to the back page real quick here. And let's do the same thing for this one. Because I want to make sure that before we start this, you get an idea of why the label on the axis matters so much. On the count of 3, based on this graph, what are the labels here? 1, 2, 3.
Temperature versus time.
Very nice. Temperature versus time. Well, how is that different from the other one? Well, in this case here, we've got temperature on the y-axis. On the other one, where's temperature? On the x-axis. Okay? On the other one, we've got temperature going along the x-axis. So now we've got temperature going along our y-axis. On the other graph, what's on our y-axis? Pressure. Is there pressure on the heating curve? Do you see anything that tells you pressure on there? No. Pressure is not being indicated anywhere on there, okay? So nowhere on there, maybe in the figure label, they may tell you what the pressure is, but nowhere on there does it say anything about pressure. In this graph, pressure is a really big deal. The entire axis is devoted to pressure. And so what we end up getting here is a really, really nice plot, and it tells us so much. The first thing I want to tell you is, I already explained to you that we read left to right. And same thing here, because you're going to need to label this, you won't be able to see it. It's solid, liquid, gas going from left to right. Your furthest on the left side will be solid, then this will be liquid, and then all the way on the right will be a gas. Got it? That's the first thing. So if you can't see it on yours, go ahead and put an S, an L, and a G. Okay? Go ahead and write those in. All right, so I was telling you about water. Here's the coolest thing about this. Typically, most substances do not have open arms, okay? The slope here would actually be to the right, going like this for almost every other substance. And this is important because if I were to increase the pressure, and I had a liquid, okay? And I start to increase the pressure on my liquid, increase pressure, what's happening to the molecules? They're getting what to each other?
Closer together.
Closer and closer. And if they're getting closer and closer to each other, then eventually what would you expect to happen to your liquid? It would turn into a solid. Okay, that makes sense. So you can see here that if you have a liquid and you increase the pressure on the liquid, increase the pressure on the liquid, increase the pressure on the liquid, eventually you could get solid. If this was my line, okay? Notice how water is different. So let me erase this line for just a minute here. And if I erase this line and we look at what water does, is there any point on the graph where I could increase my pressure, staying at a constant temperature, and I could get my liquid to convert into a solid? Could I ever get my liquid to convert into a solid? No, not by increasing pressure. How could I get my liquid to turn into a solid? What is going left? Decreasing my temperature. The only way for water, in order to change a liquid into a solid, is actually by changing my temperature, okay? And the reason why, well, that happens, I guess that's indicative of the fact that we said that that's why ice does, or the solid water does what above the liquid?
Float.
It floats. Perfect. It floats. And that's why. What we ended up saying was those solid molecules, when liquid water comes together, when you increase the pressure on the liquid water, it doesn't actually turn into a solid. If you were to decrease the temperature on it, what ends up happening is the molecules start forming those crystals that we talked about that happen in the solid state. And what did we say about in water, what's true of those crystals? They actually have more what in between? More space in between. There's more space in between those molecules than there is in the liquid phase. And so if we look at this diagram on here, and we go to water, so we've got water in the gas state, water in the liquid state. When you change it into the solid state, we see that there's actually more space in between, and so that's why with water, the solid ends up floating above its liquid. Okay, so I wanted to make sure that you were aware of that water really is the only one that has a graph that looks like this. Typically, this line, this solid liquid line would be on this side. So let's talk about these lines, okay? First thing is, I think yours is labeled, so we've got an A, B, C, D, is it E and F? Does that look right? A, B, C,
Yeah.
D, E, and F. Okay, so let's start off first and let's start to label these. So this here, where A is starting as a solid and it's turning into a gas. So let's write solid turning into a gas. Do you remember what that's called? What is that phase change called? Subliming. Perfect. Sublimation, so that's subliming. Very nice. What is B then? What's happening? You're changing from what to what? Gas back to solid. Very good. Gas back to solid. And what do you call that?
Deposition.
Good. Deposition. We're going to say depositing. Very good. Nice. See? So now we're starting at a solid and we're going to what? Liquid. What do you call solid to liquid? We all know this. Melting. Very good. And then going back the other way is liquid back to solid. What do you call that?
Freezing.
Freezing. Very good. They'll also call it solidifying. They may call it crystallizing, but crystallizing is typically when you evaporate water off and you're left with the solid behind. What about E? What phase are you going from what to what? Liquid to gas. Very good. Liquid to gas. And what is that?
Vaporization.
Yep, either boiling or vaporizing. And the other way is called what? So gas to liquid. Very good. Condensing. Awesome. And condensing. Very good. Okay, so a couple of things here. You need to make sure that you can fill out this chart yourself. Okay? So be able to label all the arrows. And not only that, let's talk about this line right here. This line here is called the solid liquid equilibrium. Okay? And where your solid liquid equilibrium is, you could actually, this is crazy, you could actually have melting happen at any point on the line. Okay? This line here, I'm just going to kind of do slashes for this one instead. This one here, this is called your liquid gas equilibrium. And anywhere along this line, you'll actually get boiling. And this one down here is your solid gas equilibrium. And again, on there, you could either get subliming or depositing, depending on your environment surrounding. But right along this line, if you're at this pressure and this temperature going up and down on your graph, then that means that it would be subliming right on there. If you could stay at that one temperature, it would be subliming, okay? And depositing at the same time, if you could stay at that temperature. So what's the significance of this dotted line that goes across here? What's the significance of that dotted line going all the way across? What does 1 ATM represent? What word did we say?
Atmosphere.
Say it loud. Normal. Awesome. Remember when we said this is what would be called normal. So anywhere on this line you can get melting. But if you're at this point right here, this point right there is called your normal freezing point or melting point. Okay? So then what do you think this one is called right there? What do you think that point is called? Normal boiling point. Perfect. That's called your normal boiling point right there. So if you're at 1 atmosphere pressure, then that's where normal is. But really, you can get boiling anywhere along this line, okay? So as long as you're at this temperature and this pressure, you match that up, your substance will be boiling, okay? And in this case, it's water. It'll be boiling at any, you could figure out, if you said, okay, I'm going to create a vacuum and I'm going to decrease my pressure to a certain amount, and you want to find out what temperature you need that water will boil, you could literally just come across the line and come down and figure out where you can get water to boil at 50 degrees Celsius. As long as you're at the right pressure, you can get it to boil, okay? So that's the coolest thing about what this graph does. And so you could come down and figure, well, normal would be 100 degrees Celsius for water's boiling point. And water's normal freezing point is what? 0. Perfect. It's 0 degrees Celsius. Okay, last thing is, well, actually, it'll say in the blanks here. So the line separating two phases where the substance is in equilibrium between the two phases, we talked about that. The triple point, did you find the triple point? Where is the triple point? Yep, that's where all of them meet right there. And so they say that the triple point is the only set of conditions at which all 3 phases, very good, exist in equilibrium. All 3 of them. So you would have, if it's water, what would that look like? It would look like slush, and you would actually get like a steam, like a vapor above it. Okay, maybe you've seen that before. Okay, so that's where you would have all 3 phases. Okay, we already labeled it. Last thing is this critical point. The critical point is there because if you were to surpass this point, you will no longer get your gas to turn into a liquid. No longer be able to get that. So it doesn't matter how much you increase your pressure on your gas. You can increase your pressure on your gas all you want. It will not change into a liquid anymore, okay? And so that's what the critical point is basically telling you. All right, so now let's just talk about the heating curve. The energy required to cause substances to melt and boil and disrupt their forces of attraction, it comes from everything around. So we're just going to call that the environment surrounding. The environment surrounding. So, for example, if you took a piece of ice and put a piece of ice in your hand, what would you notice? What would happen to your hand? It starts to get cold. Why? Why does your hand get cold? It's taking your energy away from you. And when it takes the energy away from you, what happens to those molecules? Yeah, they're able to do what? Turn from solid into liquid, which is what we call melting. Okay? And so the molecules now are able to flow past one another, and so you can get melting to happen. So the energy required to melt the ice, it's just going to come from your hand. That's where it's coming from. It's coming from you. How does your hand feel? We said it feels cool. If the energy is being absorbed by the ice cube, then what do you call the process? It's taking your energy away and it's absorbing the energy. We say that's endothermic. Awesome. We call that endothermic. Perfect. Okay. So the heating curve of water, we already said this, but this is a temperature versus time graph. Temp versus time graph. And this shows plateaus. Do you remember what these plateaus mean? The plateaus are where the molecules are doing what? It's constant temperature, and they're changing what?
Phase.
Changing phase. Perfect. So this is where the molecules change phase. So let's make sure that you can label a heating curve. So it's different from a phase change diagram. So now we've got the heating curve. So here we've got A, B, C, D, E, and F. Between A and B, if it's just ice, then you would just say the substance is in what phase? Solid. Solid, but you're heating up the solid in this case, between A and B. And between B and C, what do you have happening? Melting. Solid to liquid. Perfect. Solid is converting to liquid, and so we're going to call that melting. Perfect. What happens between C and D? Heating what?
Liquid.
Only the liquid. This is only liquid, okay? And so you're heating up the liquid, only heating the liquid. What happens between D and E? Now you reach a point where your liquid starts to do what? Change to gas. So now we've got liquid to gas, and so we call this, yep, either vaporizing or boiling. And last one, E to F, is what? Only gas. This is only gas now. And so you're going to be heating the gas up. Okay. Again, depending on whether or not your environment surrounding is colder or hotter, then you could be going the opposite direction. All right, and that's basically it for heat